M. Balaji, Assistant Professor of Physics, Saurashtra College. I am a participant of first online refresher course in physics organized from 7th September 2020 to 20th September 2020 by UGC Human Resource Development Center, Gujarat University, Ahmedabad. I am going to deliver my presentation on synthesis and characterization of superparamagnetic Core-Shellnanocomposites for biomedical application. In general, superparamagnetic nanoparticle, which is nothing but it's a single domain nanoparticle which is very much useful in biomedical application, particularly for cancer diagnosis, drug delivery and hyperthermia treatment. In hyperthermia treatment, the drugs are superparamagnetic drugs are given to the patient, and that is diagnosis by endoscopy. The pathway of the drug which is identified by the endoscopy technique. When that is reached to the tumor cell, immediately the AC field which is applied on the patient, so immediately that will induce the magnetization inside that patient, which creates the thermal energy, that thermal energy which is used to destroy the tumor cell. It's a very important technique. Currently with the chemotherapy treatment, hyperthermia treatment is very famous to destroy the tumor cell for cancer. Similarly, the superparamagnetic single domain nanoparticles are very much useful in cancer diagnosis and drug delivery system. Meanwhile, in magnetic resonance imaging technique, the high field magnetic coils are manufactured by superparamagnetic nanoparticle, because easily you can get a high magnetization value with a very short of time. So that is very important and necessary for magnetic resonance imaging. That's why which is very much useful in MRI scan. Similarly, in tissue engineering, to make a artificial bone and cell growth, these magnetic nanoparticles are very useful. In this presentation, we are going to synthesize superparamagnetic spinal copper ferrite nanoparticles. The important the tendency of this magnetic nanoparticle, which is easily get agglomerated to each other. That is mainly because of its dipole-dipole interaction and surface to volume ratio. So to avoid the agglomeration, we must keep some coating on the surface of superparamagnetic nanoparticles. Here we are trying to coat a polyaniline nanopolymer on the surface of the copper ferrite element. Successfully we have synthesized the Core-Shellnanocomposites, and the addition of polyaniline, which creates the high conducting behavior. Meanwhile, that is very much useful to tune the magnetic behavior of the ferrite element. To fabricate the core shell structured copper ferrite polyaniline nanocomposites, here we are taking three different compositions. One is 83% of copper ferrite adding with 17% of polyaniline, then 71% of copper ferrite added with 29 weight percentage of polyaniline, and 62.5% of copper ferrite which is added with 37.5% of polyaniline. So there are three important composite compositions has been maintained, that is mentioned as S1, S2 and S3 respectively. So to synthesize a polymer material of core shell composites, here we adopted in situ polymerization technique. For that, first 0.1 mole of sulfuric acid which is vigorously stirred at room temperature for 10 minutes. Then 0.1 mole of distilled aniline monomer which is added with the copper ferrite element. Then the aqueous ammonium peroxide sulfate which is added dropwise with the above set solution. That creates the polymerization reaction. Within 30 minutes with the constant stirring, we can get polymer of Core-Shellnanocomposite. But the final element which has the high rating of sulfuric acid, That's why we are using 0.1 mole of sulfuric acid finally to replenish the sulfate ions which is in a polymer chain. So the final element which is dried with 110 degree Celsius for 2 hours to remove the remaining solvents. The mechanism behind this core-shell formation is the copper ferrite which prepared from the co-precipitation technique, which is in less than or equal to 7 pH value, which means the metal ion is highly positive charge. So in the presence of high acid medium, like here we are using sulfuric acid, so the sulfate ions of a highly negative charge element, the sulfate ion is totally covered on the surface of the copper ferrite element. Then in the meantime, during the polymerization reaction, the polyaniline monomer which is converted into anilium cation during the polymerization reaction. So that anilium cation which is covered on the surface of these negative ions, and polymerization reaction which will be occurred in the presence of oxidizing agent ammonium peroxide sulfate. So we can get a core shell element. Inside we have a core of copper ferrite, then the outer surface is totally covered by polyaniline. So it is the mechanism we propose to synthesize the core-shell nanocomposites. As I said, it's the first time we used Raman spectra with different energy values to confirm the core-shell nanocomposites. Here we used 632.8 nanometer wavelength, which is in red part of visible line from the helium neon laser. The diameter we maintained as a constant 1.86 microns, and initially we used 0.3 milliwatt of laser power to confirm the outer shell element like polyaniline element. Then we used 3 milliwatt high energy laser to confirm the induced thermal effect as well as the core element. Finally, the induced thermal energy during that high energy laser Raman spectra, to confirm that induced energy, we annealed the sample at 3 different temperatures, 200, 300 and 400 degrees Celsius for 2 hours, and we measured the Raman spectra at low energy 0.3 milliwatt. We confirmed the presence of the core shell element. Actually, we tried with different input powers starting from 0.1 to 4 milliwatt with a step of 0.1 milliwatt. So finally we concluded these two characteristic input power which entirely distinguish the presence of core shell structure. Here you can see the low energy Raman spectra of the copper ferrite, polyaniline and 3 different composites S1, S2 and S3. So here you can see in a copper ferrite you can see a characteristic behavior of copper and ferrite element, and in the polyaniline you can get a characteristic behavior starting from 1647 centimeter minus 1 to 415. There is no resemblance because this is pure polyaniline, so there is no characteristic behavior of ferrite. In the addition of polyaniline with the copper ferrite, which is low concentration of polyaniline in S1, which shows a minimum peak behavior of copper ferrite here. Similarly, the polyaniline characteristic behavior also present in this S1. So when you increasing the polyaniline concentration, the polyaniline characteristic behavior is presented along with this characteristic behavior of the minute characteristic behavior of ferrite element. Similarly, S3 also, but here there is no characteristic behavior of spinal cubic ferrite element exactly at 295 centimeter minus 1. There is no maximum intense characteristic peak of this copper ferrite which is present in S1, S2 and S3. So from that we can conclude which gives the exact behavior of only the shell element. that is not penetrated inside the core element, so which gives only the characteristic behavior of polyaniline shell, because here we are using very low energy, 0.3 milliwatt. Next, this is the characteristic assignment of different peaks what we are getting from the Raman spectra of low energy. Here it's the high energy Raman spectra. Here you can see the same element, but here we are using 3 milliwatt laser. So when you use the high energy laser beam, the laser beam is penetrated on the surface of polyaniline. Here you can see a copper ferrite characteristic behavior, and here polyaniline characteristic behavior. In the low concentration of polyaniline in S1, the total polymer chain is destroyed. That is mainly because of the induced thermal energy during this high energy Raman, right? So similarly, when we are taking the high energy Raman spectra for S2 and S3, there is also a change in behavior, totally destroyed polymer chain, so which conforms, but in this case here you can see the copper ferrite characteristic behavior, so which conforms inside the core are present, and polymer which is very weak, that's why easily that can be penetrated on the surface. To confirm this induced thermal energy, we had taken Raman spectra for 3 different annealed samples. Here also you can get the same characteristic behavior as we are receiving, almost nearly characteristic behavior what we are receiving from the high energy Raman spectra. The XRD analysis also confirms all the peaks except copper ferrite, which shows only the amorphous in nature. The copper ferrite, which gives clearly it's a cubic spinal element. From the HRSEM analysis, which confirms in the copper ferrite, it gives a agglomerated nature, where are very smaller elements are presented with the size of 10 to 12 nanometer, but almost all the particles get agglomerated. In polyaniline, we have seen a very clear spherical particles that is marked here, which is around 30 to 40 nanometer. The copper higher concentration, in the case of S1, all the particles get agglomerated. There is no spherical particles, because here copper ferrite is the dominating behavior, and the polyaniline is very, very low concentration. Similarly, when you increasing the polyaniline concentration, the particle size which is get increased, which is around 88 nanometer, and when you increasing the polyaniline concentration more, the spherical nature of the behavior which is increased, and the average particle size is 98 nanometer. The MH measurement of the copper ferrite and the nanocomposites, which shows a superparamagnetic behavior exactly at zero coercivity, and the saturation magnetization is decreased while increasing the non-magnetic polyaniline concentration. Here it's a thermomagnetic measurement of copper ferrite and nanocomposites. When we increasing the polyaniline concentration, the knee point value is get decreased continuously, which shows a non-magnetic behavior of a polyaniline material. In summary, we can conclude we have first synthesized a copper ferrite polyaniline nanocomposites by using in situ polymerization technique with different compositions, and the core-shell structure which is confirmed by Raman spectrometer with different energies, and that is also confirmed the characteristic of XRD, FTAR and HRSEM analysis also confirmed the synthesis of core-shell nanocomposites. Thank you. I, Dr. M. Balaji, thank UGC Human Resource Development Center of Gujarat University, Ahmedabad for providing me an opportunity to join first online refresher course in physics. Thank you. Thank you very much.